The bridge is in place. The cumulative distribution function, one function that describes any random variable, staircases for the discrete, smooth progressions for the continuous. In this video, we differentiate that smooth function and meet the density, the working object of the continuous world for the rest of the course, read the probabilities of intervals as areas under it, and see why single exact points carry no probability at all. Then rebuild expectation on integrals, where the mean and the variance survive word for word, and finish with a trick that computes a mean from tail probabilities alone. Take a continuous random variable, one whose CDF is a smooth function, differentiable almost everywhere. Its derivative gets a name, the probability density function f of x, the slope of the CDF at each point. Where the function climbs steeply, the density stands tall. Where the function flattens out, the density falls back towards zero. And the fundamental theorem of calculus runs the definition backwards. Integrate the density from minus infinity up to x, and the CDF reappears. Differentiate to go one way, integrate to come back. Watch the two functions together, the CDF above, its density below. Slide a point x along the axis, and the shaded area under the density up to x always matches the height of the CDF. Height above, area below, the same information, stored two ways. That reading turns last video's interval formula into a picture. The probability that x lands between x1 and x2 is the CDF difference, which is exactly the integral of the density across the interval. Probabilities of intervals are areas under the density curve. Where the density runs tall, the variable lands there often. Where it hugs zero, it almost never does. The density spreads probability along the line the way the mass function once stacked it on points. The area picture answers a natural question with a surprise. What is the probability that x hits one exact value? Take a strip under the density from x1 up to x2 and slide x1 upward. The strip narrows, its area drains away, and in the limit nothing is left. For a continuous random variable, the probability that x equals any single point is exactly zero. A useful corollary follows at once. Open or closed, endpoints never matter. All four interval probabilities agree. And a warning worth its own frame, f of x is not the probability that x equals x. It is a density, probability per unit length. A tall, narrow density can rise far above 1, squeeze the same unit of area onto a thinner base, and the height must grow. Only areas are probabilities, never heights. The axioms survive the translation. The variable lands somewhere, so the total area under the density is 1, normalization, in its new clothes. Probabilities are non-negative, so the density never dips below 0. And for any admissible set S, the probability that x falls in S is the integral of the density over S. Two conditions, non-negative and total area 1, and a function essentially qualifies as a density. That is all it takes to specify a continuous model. Expectation crosses the bridge the same way. In Chapter 6, the expected value of g of x weighed each value by its probability, mass, and summed. Replace the sum by an integral and the mass by density times length, and the sentence survives word for word. The expectation of g of x is the integral of g times the density. Every tool from that chapter rides along for free. Set g to the identity and the mean appears the integral of u times f of u. The variance is the expected squared distance from the mean, exactly as before. And the shortcut still holds, the mean of the square minus the square of the mean. But the continuous world offers one genuinely new tool. For a non-negative random variable with finite mean, the mean is the integral of the tail. Integrate the probability that x exceeds x from 0 to infinity, a mean computed without ever touching the density. The proof is a change of perspective. The tail integral is a double integral over the region where u exceeds x, swept in vertical strips, one for each x. Sweep the same region in horizontal strips instead, and each strip runs from 0 up to u, so it contributes u times f of u, the integrand of the mean. Same region, two ways to sweep it. Tails on one side, the mean on the other. Let the tail formula show off. A player throws darts at a circular target of unit radius, and every dart lands uniformly over the disk, probability proportional to area, the geometric models from early in the course. How far from the center should we expect a dart to land? Call the distance r and pick a radius r. The dart lands beyond r exactly when it falls outside the inner disk of radius r, and for a uniform dart, probability is area ratio. The inner disk has area pi r squared out of pi, so the tail is 1 minus r squared. That is everything the tail formula needs. The expected distance is the integral from 0 to 1 of 1 minus r squared, which is r minus r cubed over 3, evaluated at 1/2. Notice what never appeared, the density of r. The tail was pure geometry, and the tail formula turned geometry straight into a mean. The key idea of this video: the density is the CDF's slope, probabilities are areas under it, and expectation rides the same integral. Next up, the distributions everyone uses, the uniform and the Gaussian.